Okay, so in this video we will talk about complex numbers, we'll give some properties, and then we will give some background on linear algebra, only what's necessary. Okay, so in quantum computing, complex numbers play a major role. A complex number is a number of the form z equals a plus bi, where a and b are real numbers. I here it's equal to the number square root of -1, so it's an imaginary number. So I squared is equal to -1. I cubed is equal to I times I squared, and that's equal to minus I. I to the fourth is equal to 1. So in fact, the general formula is that I to the n is equal to I to the n mod 4. So in quantum computing, the probabilities of states and transitions are given in the form of complex numbers. Recall from the double-slit experiment that we measured the energy level of an electron or of the proton on the panel. Well, we didn't really measure the probability of the electron hitting on the panel, but that distribution gave us the amplitudes. So we call them amplitudes instead of probabilities in quantum mechanics. So they're given in the form of complex numbers. So as to that, if z is a complex number, then magnitude z squared is equal to a squared plus b squared. And this is a real number between 0 and 1. Okay, this is an element of real number, and it's between the interval 0 and 1. So we call magnitude z the modulus of z. And in this case, magnitude z is equal to, from the equation above, it's equal to square root of a squared plus b squared. But you may ask, well, why do we use complex numbers? Why do we need them? There are two reasons, one of which is the necessary reason. The necessary reason has to do with time evolution of quantum systems. So this goes back to Schrödinger's equation. We need to use complex numbers because of the time evolution of complex numbers and how they are defined. But the auxiliary reason is that real number probabilities don't necessarily add together to obtain larger real numbers. Okay, so that's why complex numbers are it's more easy to simulate the property of interferences and so on with complex numbers. Let me demonstrate this with an example. So if P1 and P2 are two real numbers, so suppose P1 and P2 be two real numbers. Okay, so and each pi is a real number between 0 and 1. Okay. Now, since they are real numbers, necessarily P1 plus P2 is larger than or equal to P1, or P2 for that matter, right? But if C1 and C2 were complex numbers, so let's suppose that C1 and C2 are complex numbers, then we don't necessarily have this property. That is, this number, this is a real number, right? It gives us the probability, a probability value. This does not need to be bigger than magnitude square C1 or magnitude square C2. Let me give an example. Okay, so let C1 be equal to 5 plus 3i, and let C2 be minus 3 minus 2i. Okay, then C1 squared, magnitude C1 squared is equal to 34. And magnitude C2 squared is equal to 13. But then, what is the magnitude square of C1 plus C2? This is equal to 2 plus I magnitude squared, which is equal to 5. And notice that this is less than either of these probabilities, right? So this is C1 plus C2 squared is less than Ci squared, where I is an element of the set 1, 2. So with complex numbers, this is easier to define. This is easier to simulate. Of course, we can simulate this property solely by using real numbers, because ultimately a complex number, a plus bi, is a real number, is a pair of real numbers, right? So I can simulate any, I can define, describe any complex number in terms of a pair of real numbers. But this is more convenient, okay? Using complex numbers is more convenient, but the necessary reason for using complex numbers has to do with time evolution and reversibility condition. All right, so the complex conjugate of a complex number is denoted by z star, and this is simply inverting the sign of the imaginary part. Okay, so what we're really doing is just a reflection around the real axis. So we will denote the set of real numbers by this R letter, and we'll denote the set of complex numbers by this C letter. Okay, so these are known. Now we can transform any given complex number given in the Cartesian coordinate form into polar form, right? So if z is a complex number a plus bi, okay, we can represent this complex number by polar coordinates. Rho and theta. Here rho is called the magnitude and theta is called the phase. Okay, so it's like having an angle. So we can represent this by a vector. Okay, and all we need is just an angle and the magnitude, the length of the vector. Okay, so how do we transform to polar coordinates from Cartesian coordinates? Well, given a and b, rho is simply equal to, from elementary trigonometry we know that rho will be equal to a squared plus b squared. And theta is the angle, and that's equal to arc tangent b over a. Okay. And how do we go back from polar to Cartesian representation? Again, by the use of trigonometry, given rho and theta, a will be equal to rho times cosine theta, and b will be equal to rho times sine theta. Okay. All right, so in the lecture notes, I give the definition of vector spaces, vectors, linear maps, linear combinations, bases, spanning, and so on, inner products. I'm not going to define them. So I assume that you're familiar with the notion of vector spaces, particularly complex vector spaces and inner products and bases, linear independence, and so on. One thing to remember about inner products is that when the inner product of two vectors is 0, that means they are orthogonal. In fact, that's the definition of orthogonality. Two vectors are called orthogonal if their inner product is 0. We denote the inner product by this bracket notation. So if x and y are two vectors, then this bracket notation denotes the inner product of x and y. Okay. Okay. A set of vectors is called orthonormal if every vector in that vector space is pairwise orthogonal and is of unit length. What do we mean by unit length? Well, simply the norm of the vector is equal to 1. The norm of the vector, so if v is a vector, okay, then the norm of v is defined as the square root of the inner product of v with itself. Okay. So this is the norm, the length of v. And if the norm of v is equal to 1, then the vector v is called a unit length vector. All right, so an orthonormal set of vectors is a set in which every vector in that vector space is pairwise orthogonal, and they're all of unit length. Okay, so a special kind of vector space called Hilbert space will be of special interest for quantum computing. We will be dealing with only finite spaces. Okay, finite vector spaces. So a complex inner product space, which is finite, is also called Hilbert space. So any finite dimensional inner product space is called a Hilbert space. But in fact, Hilbert spaces are more than this. An infinite space could also be called a Hilbert space as long as it satisfies some completeness property. I'm not going to mention it here, but it's in the lecture notes. But since we are only dealing with finite vector spaces, finite dimensional vector spaces, a Hilbert space can be thought of as a finite dimensional inner product space. Okay. All right. So And I assume that you know what an eigenvector and eigenvalue is. If A is a matrix, say an n-dimensional square matrix, and if lambda is a complex number and V is a vector such that A times V equals lambda times V, then lambda is called an eigenvalue. Eigenvalue of the matrix A, and V is called an eigenvector associated with lambda. Okay, so intuitively this means that when we multiply a vector with an eigenvector with a matrix, then there's no difference between multiplying that with a matrix or multiplying that vector with a scalar. Okay. All right. So, given an n-dimensional square matrix A, the adjoint of A so this is another definition. If A is a square matrix, the adjoint of A, this is denoted by A dagger, and this is equal to A transpose conjugate. The conjugate of A transpose, or the order doesn't matter actually. Okay, and A is called unitary if the multiplication of A and A dagger is commutative and it's equal to the identity matrix of dimension n. Okay, so we'll be using unitary matrices quite often in quantum computing. Okay, unitary transformations, unitary operators will correspond to a computational step, in fact. Okay, so we will talk about this later on more. But consider now, if I want to combine two systems into one, okay, so remember the marble example that we gave in the previous video. Okay, now imagine we want to combine those two systems into one. How are we going to do it mathematically? Well, what we call tensor products is one way to combine two or more different systems into one. Okay, so we use tensor products in this case. Tensor products. So tensor products are used to combine multiple systems into one single compound systems. Okay, so this is similar to matrix multiplication, except that it's a bit more different. So the tensor product of, let's say, R by S and T by U matrices. So given two matrices, one is of dimension R by S. Okay, so this is A11, A12, A1S, A21. So this is ARS, A2S. And given a matrix B, which is of dimension T by U, B11, B12, B1U, BTU. The tensor product of A and B is denoted by AO times B. It's denoted by this notation. And this is equal to an RT by SU matrix. Okay, so what we do is that we multiply each entry of A with the matrix B. So we multiply A11 with the matrix B. And then the next entry will be, we multiply A12 with the matrix B. Okay. So in fact, each entry of AO times B is a T by U matrix. Okay. So we have a T by U matrix here. Okay. So this is a R1 B, a R2 times B, and here we have a 1S times B, and lastly we have a RS times B. Okay, so it's an RT by SU size matrix. And let me give an example, a concrete example, so that you'll understand better. Now, imagine that we have two systems, a red marble system and a blue marble system, okay? So imagine we have a blue marble and a red marble system. Okay, now the blue marble system, let's suppose that it's a 3-vertex graph, okay, whose vertices are labeled as A, B, C, okay. Blue marble system. It has vertices A, B, C, okay, and let's suppose that it has the adjacency matrix defined as 0, 1 over 3, 2 over 3, 1 over 6, 1 over 2, 1 over 3, 5 over 6, 1 over 6, and 0. Imagine also a red marble system placed on another separate graph, okay? And let's suppose that the vertices in the red marble system are labeled as 0 and 1, okay? So it has two vertices labeled as 0 and 1. So let's label the vertices as 0 and 1. And assume that we have the adjacency matrix in the red marble system defined as 1 over 3, 2 over 3, 2 over 3, 1 over 3. So notice that the outgoing and the incoming edges preserve normality, okay? So the system is normalized. The summation of the weights of the outgoing and incoming edges are both equal to 1. Okay, so then what about the dynamics of the compound system? Okay, suppose we want to combine these two systems, the red marble and blue marble system. So let's take the inner product of the blue marble system and the red marble system. the dynamics, the adjacency matrix of the compound system will be M tensor N, right? And this is equal to, so 0 times the matrix N, right? And then we have 1 over 3 times N, 2 over 3 times N, 1 over 6 times N, 1 over 2 times N, 1 over 3 times N. Here we have 5 over 6 times N, 1 over 6 times N, 0 times N. Okay, so each entry here is a 2 by 2 matrix. So this is simply the 0, 0, 0, 0 matrix. Okay. I'm not going to write them all, but just try to write them explicitly as an exercise. Okay, so then it is a 6 by 6 matrix, in fact. So M tensor N is a 6 by 6 matrix. Okay. So what about the state of a combined system? Okay. So now let's suppose that the blue marble system is in state B, let's say 1 over 3, 1 over 3, 1 over 3. Okay, and let's suppose that the red marble system is in state R equals 1 over 2, 1 over 2. Okay, so let's pick up the numbers in the most convenient way. Okay, so the combined system, the state of the combined system will be then B tensor R. Okay, and this is equal to all 1 over 6, 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 and 1 over 6. Okay, so it's a 6 by 1 matrix. So what does that mean? So, okay, so we assume that the vertices of the blue marble system were denoted by A, B, C, right? A, B, C. The vertices of the red marble system were denoted by 0, 1. So when we take the tensor product, we get all the combinations. So then the first entry of this vector, this combined vector, the first position will denote the vertex A0. Okay. The next one will be A1. Next one will be B0, B1, C0, C1. Okay, so note that this denotes the state of a combined system. So the vertices will consist of all these combinations. Okay, and this corresponds to the fact that this means that there is a 1 over 6 chance of the blue marble being on vertex A and the red marble being on vertex 0. Okay, so this explains the first entry. And furthermore, it means that there is a 1/6 chance of the blue marble being on vertex A, but the red marble being on vertex 1. And then there is a 1/6 chance that the blue marble being on vertex B and the red marble being on vertex 0. Okay, so similarly for the others. And this is, that's what it denotes. So as you can see, given n many systems, we can take the tensor product of those systems and get a combined system, a compound system. And the state of the compound system will denote, it will describe the state of the entire system, okay, when combined into one. Okay, so this was the introduction chapter. I'm hoping to move on to the second chapter, the basic quantum theory. And so I'll see you in the next video.